So the first we are going to look at is a shorted load, right? So the load resistance is 0 ohms. It's not a complex load, it's just 0 ohms and J0. So the reflection coefficient for this is -1, right? So we are looking at an animation where I have a sinusoidal generator. I have Z0 series resistance connected to a transmission line. The length of this transmission line is 2 lambda as indicated by the extent of these plots, right? At the end of this transmission line, I basically have different loads, and in this case I have just shorted it to ground, right? Okay. So how would I get lambda? If I know the omega in the problem, I can get beta is omega square root of LC, right? And lambda is 2 pi by beta. Okay. So I have taken a very specific length of the transmission line of 2 lambda. I have connected a generator voltage of 1 volt amplitude, right? So it is 1 volt cosine of omega t, right? I apply this voltage on the transmission line, and I am basically looking at what is the net voltage, right? So remember that if I were to take a multimeter and place it between the central conductor and the outer conductor along this transmission line, and anywhere along the transmission line if I choose, I will essentially see the voltage corresponding to V total, right? So the blue curve in the second plot, right, is an indication of the net voltage, right? And we want to understand or describe this net voltage in terms of equations, which is what we did all along this week, right? So this is a visual animation to show you how this voltage varies in time and along distance, right? So even though I say that this is V of t, we are actually getting to see V of x comma t, right? So this is where the load is, right? To the right of the plot is where I have the load, and to the left I have the source, okay? And essentially this V total is the incident and reflected, right? So the red curve on the top plot is showing the incident wave, and the green is the reflected wave. So I'll play the animation, and you can see why we call the red voltage as the red curve as the incident voltage, because it will look like it is moving to the right, right? So remember, this is the wave phenomena. Think of it in that sense, that you will notice that to our eyes, when we play this in a video form as an animation, it will look like the red curve is moving to the right and the green curve is moving to the left. We cannot quite measure these incident and reflected voltages, right? Because when I take a multimeter and measure it, I measure only the blue curve, which is V total. But we can always decompose. We can decompose and say that this blue V total curve is the sum of the red and the green curve, right? So V total is essentially the incident plus reflected, right? So in this time domain analysis for a single frequency excitation, hopefully this animation stands as a good picture, right, for what is happening along the transmission line. Even though the red and the green curves cannot be quite separated in a given transmission line, what we measure is the V total. we can decompose it into these incident and reflected waves, because it makes for convenient mathematics to make quantitative predictions of what V total is going to become. And the envelope is essentially the maximum that the voltage will take, right? The maximum and the minimum values that a voltage will take at any given point along the transmission line. I am just drawing that as an envelope, right? So let us play some of these animations, and hopefully it will give you a flavor of what is going on in this transmission line. So you can notice that the red curve looks like it is moving to the right, green curve is moving to the left, and because the reflection coefficient is 1, at the load end where the distance is 2 lambda, the value of the function, green function, and the value of the red function are always different by a factor of -1, right? So if it is +1 volt for the red curve, you will see that the green function takes -1 volt, right? And looking at the net voltage, you can notice that there are points along the transmission line where there is no oscillation in voltage or current, right? So these are what we call nodes, right? And the points where there is maximum fluctuation, we call them antinodes. Antinode, and this is your node. And I have used the point at lambda, this black dot, right? So for the subsequent animations, I want you to look at the black dot. That black dot would essentially be the measured voltage, right? Say using a multimeter in real time, right, to measure the voltage. Follow the black dot. In this particular case, for a shorted line, at the center of the transmission line, we find a node. So there is no movement, right, or the voltage is essentially 0 for all times at that particular location. And that's not the only point. We also notice that at 3 lambda by 2 and lambda by 2 also there are nodes. This should be further reaffirming what we saw in terms of algebraic equations before, that is, we see periodic behavior, right, by a distance of lambda by 2, right. So the distance between two nodes is lambda by 2. Similarly, the distance between two antinodes is also lambda by 2. So we see the same behavior along the transmission line between 2 points that are separated by lambda by 2, right. All right, next we will move to the load for open circuit. Okay, now observe how it is different for an open circuit. So at open circuit, the reflection coefficient is 1, right. So you will notice that the red curve for the incident wave and the green curve for the reflected wave will have the same value at the end of the line at 2 lambda, right. So notice this time we see something different. It kind of looks like the shorted case, but it seems like it has got a shifted version of it, right. So the voltage seems to have the highest amplitude of oscillation at the open circuit, right, because the current is 0, right. So you would have maximum voltage fluctuation there for a reflection coefficient of 1. We still see the same periodicity, but now at lambda, instead of having a node, we have an antinode, right. So at the middle of the line, we have the maximum fluctuation in voltage. So now we will go to the next load, which is the matched load. Okay. So for matched load, remember the reflection coefficient is 0. So in this case, it's a very simple simulation or animation. You will just see that there is an incident wave and no reflected wave. So your total voltage and the incident voltage will be the same. and you can notice that the envelope is constant and there is no standing wave phenomena, right? Because there is no two waves to constructively or destructively interfere. You notice that power is just being delivered from the source to the load. Okay, so you can always rewind this video multiple times if you want to look at any particular loads carefully. Next we will go to something that is intermediate, right? So neither it is open or short, which is the cases for maximum magnitude of reflection coefficient. There is the matched load where the reflection coefficient is minimum at 0. So we'll take two examples where it is somewhere in between. So we'll look at 25 ohms. So you can notice that the reflected wave is not quite as strong as the incident wave because the reflection coefficient is about 1/3, right? So the height of the green curve is 1/3 of the height of the red curve. But you can also take a look at the V total and the envelope, right? So there are points of maximum and minimum voltages, right? And you can say that the ratio of these two voltages, so this would be the V max, this would be the V min, and your voltage standing wave ratio is V max by Q. Right? So you can see what we mean by the voltage standing wave ratio. In the case of open and short circuit, V min was 0. Right? We had perfect nodes and antinodes. So what do you think the voltage standing wave ratio will become? Because V minimum is 0, it will become infinite, right? And for the case of the matched load, we saw that the standing wave ratio was 1. So now we have some number between 1 and infinity for the voltage standing wave ratio for a load of 25 ohms, which gives a reflection coefficient of -1/3. Lastly, I'll just show you what it is for 100 ohms, which is a reflection coefficient of +1/3 as opposed to -1/3 for 25 ohms. You can also see how the voltage is actually changing as a function of both position and time along the transmission line. And you can notice that the amplitudes are not quite the same along the transmission line. There are points of high fluctuations and points of low fluctuations. Okay. All right. With this, I think we can wrap up with understanding of constructive and destructive interferences of sinusoidally fluctuating voltages along the transmission line. We looked at impedance transformations. We looked at the periodicity. We introduced a concept called voltage standing wave ratio. And we looked at how one can actually go through using the rigorous mathematics for a single frequency analysis of a transmission line using the distributed model to describe the voltages and currents at any point along the transmission line. Okay. Now, in the next week, we will see how we can make use of all that we have learned and put this knowledge to use in some practical circuits in some way. Okay. Thank you.